Space exploration has always been a daring venture, but the stakes feel higher than ever as SpaceX prepares for its 10th test flight of the Starship rocket. This massive spacecraft, designed to carry humanity to the Moon, Mars, and beyond, is on the brink of another critical trial that could redefine space travel or expose new challenges. With recent setbacks casting a shadow over the program, the upcoming launch from Starbase in southern Texas isn't just another test. It's a pivotal moment that could shape the future of spaceflight. But here's where it gets controversial. Can SpaceX overcome these hurdles, or will the pressure to meet deadlines compromise safety and innovation? The 10th test flight is scheduled for no earlier than Sunday, August 24th. With a 1-hour launch window opening at 6:30 p.m. CDT, 7:30 p.m. EDT, 23:30 UTC. This mission comes 3 months after a previous test flight encountered multiple issues and 2 months after an explosion on a test stand destroyed the ship originally intended for this flight. For this attempt, SpaceX will use Ship 37 as the upper stage and Booster 16 as the first stage. According to SpaceX, the upcoming flight aims to push the boundaries of what the Super Heavy booster can achieve. Multiple landing burn tests are planned, which will provide valuable data for future missions. Additionally, the company hopes to accomplish objectives left unfinished in prior flights, such as deploying Starship's first payload, 8 large flat objects called Starlink simulators, and conducting re-entry experiments aimed at returning the upper stage to the launch site for capture. These milestones have proven elusive in the past due to persistent problems with the rocket's upper stage. A post-flight analysis of Flight 9, which occurred on May 27th, revealed that Ship 35 was lost because of a failure in the main fuel tank pressurization system's diffuser. Cameras inside the vehicle captured a visible failure of the fuel diffuser canister, located within the nose cone volume on the forward dome of the main fuel tank. While pre-flight analysis didn't predict this issue, SpaceX engineers were able to replicate the failure under flight conditions during tests at their facility in McGregor, Texas. To better understand the role of the diffuser, consider this. In liquid-fueled rockets, a diffuser controls how gas flows into the tank to prevent direct contact between the gas and the liquid surface or tank walls. Without proper functioning, warm gas can cause excessive heat transfer, increasing the amount of pressurization mass required. Both the ship upper stage and Super Heavy booster rely on autogenous pressurization, a process where liquid methane is warmed and routed through the diffuser during flight. Before liftoff, gaseous nitrogen temporarily pressurizes the tanks while connected to ground infrastructure. During Flight 9, about 3 minutes into the 6-engine burn of Ship 35 following stage separation, sensors detected rising methane levels in the nose cone. By 5 minutes into the burn, pressure in the main fuel tank began dropping rapidly while simultaneously increasing in the nose cone. Although Starship systems compensated for the drop in main tank pressure and completed the ascent burn, achieving the planned velocity and second-stage engine cutoff, SECO, the unusual nose cone pressure combined with planned venting caused the vehicle to lose attitude control. This prevented the deployment of the Starlink simulators, as high pressure created adverse loads on the mechanism responsible for opening the payload door. SpaceX used reaction control thrusters to offset the attitude problem and allow nose cone venting to continue. However, about 40 seconds later, liquid methane appeared inside the nose cone, and several sensors indicated unplanned temperature drops. These anomalies triggered automatic passivation commands, causing Starship to skip the in-space burn and vent all remaining propellant into space. The vehicle re-entered Earth's atmosphere in an off-nominal attitude, and communication was lost during entry. Final telemetry showed the craft at approximately 59 kilometers altitude over the Indian Ocean, with no violations of autonomous flight safety rules. Flight 9 wasn't the only setback for the ship upper stage. On June 18th, Ship 36 exploded unexpectedly during fuel loading ahead of a 6-engine static fire test at SpaceX's Massey test facility near Starbase. Post-anomaly analysis pointed to undetected damage in a composite overwrapped pressure vessel, COPV, in the payload bay section, leading to structural failure, propellant mixing, and ignition. To address this, SpaceX plans to operate COPVs at reduced pressure, add inspections and proof tests before loading reactive propellants, update acceptance criteria, and develop a non-destructive evaluation method to detect internal damage. New external covers will also be added for extra protection. In response to the June explosion, SpaceX developed a new rig for the orbital launch mount at Pad A, enabling fueling and static fire testing at the launch site while repairs continued at Massey. Static fire tests with Ship 37 on August 1st and 3rd went smoothly, and a spin prime test followed on August 13th after replacing a Raptor engine. If Ship 37 successfully completes its planned milestones and achieves a controlled atmospheric re-entry, it would mark a significant milestone as the first Block 2 version of Starship to do so. Previous attempts during flights 7, 8, and 9 ended unsuccessfully. As a result, SpaceX hasn't yet tested certain experimental feed shield tiles, including those with active cooling, or the ruggedness of catch fittings on the side of the ship upper stage designed for future catch attempts. The Super Heavy booster has faced its own share